Hello, everyone. Welcome if you're new, welcome back if you're not. My name is Talia, and I'm an incoming fourth year student at UCSD studying chemistry. This YouTube channel is an extra resource for anyone who wants to boost up their chemistry knowledge and wants some videos to support them. In this video, I'm going to be talking about gas equilibria and some extra calculations that you can do for equilibrium problems. So if you need some help with that topic, keep on watching. And without further ado, let's get started. All right, let's go ahead and get started with gas equilibria. Okay, so the majority of these concepts are going to be exactly the same as KC calculations, so working with concentration, except now instead of concentration, we're switching out to pressure. So we can still approximate, we're still going to set up ice tables the same. It's just that now when you have gases, you can be given concentrations or you can be given pressure. There's also an equation to convert between Kc, which is for concentration, and Kp, which is pressure. So it's Kp equals Kc times RT to the delta N power, and delta N is going to be the difference in moles of gas in the reaction. So you'll see a ton of different K values in chemistry. There's Kc, which we did with concentration, Kp, which we're now doing with pressure. There's also Ka and Kb, which you'll get into in acids and bases, Kw. So the subscript just indicates what we're dealing with. Still, the K expressions are set up the same, calculations are done the same. It's just what are we given in the problem. So we're not going to work through this problem, but this is an example of a KP problem you might be given. So I'll give you a moment to read it. So the setup is exactly the same. It's just that now we are given the pressure of NO2. So there are also some additional calculations you can do with mole fractions and partial pressures when you're dealing with KP. You don't always need to do them, but they're an additional route you can take, and they can be helpful when you're not given the pressures of the reactants and products explicitly. So in this problem, or in this video, that's how we're going to do the example problem because it's something new. And if you need to go over how to solve for pressures and K regularly, you can go look at my previous equilibrium problems because, like I said, it's exactly the same, but I just go over it with concentration. You can apply it to pressure. Here's an example problem that we're going to do. We have 2NO is in equilibrium with N2 and O2. We have a temperature, 300 K, and then we have starting moles of N2 and O2 introduced into a 6-liter container. So we have to set up an ice table and find the equilibrium pressures of each gas, and we're given a Kc. And we can assume the gases are ideal. So there are a couple different ways that you can go about this problem. You can find concentrations of everything if you want, and then like try to figure out a way to convert it back to pressure. I'm going to go straight and find the pressure. For finding the pressure, you can use the equations that I talked about here. You can also do the ideal gas law for every gas, the N2 and the O2. I'm going to use these new equations because it's something new and I haven't covered it yet, but I do think I have a video on the ideal gas law. So if you need to go back and watch that, you can. We want to try to find the pressure of N2 and O2, and hint, they're going to be the same because we have the moles of both of them. But the first step is we need to find the total pressure, and we know that our gases are ideal, so we can use the ideal gas law. And we want to solve for pressure. So the ideal gas law is PV equals nRT, P equals nRT over V. So that is going to be the 2 moles combined, so 2.90 moles. And I always like to do pressures in atmospheres, so I'm going to use the R value for atmospheres, which is 0.0821 liters atmosphere per mole Kelvin times a temperature of 300 Kelvin, and then all divided by a volume of 6 liters. And then our answer, once you plug it into your calculator, is going to be 11.9 atmospheres. Okay, so now we need to find the pressure of N2 and the pressure of O2. I'll write it over here. So the pressure of N2 is going to equal the pressure of O2, which is going to be the total pressure times the mole fraction of one of them, which is going to be the N of, let's just say N2 over N total. So let's write that down. So P of N2 is going to equal P of O2, which is going to be 11.9 atmospheres times the moles of N2, which is 1.45, also the same as the moles of O2, so that's interchangeable. And then the total is 2.90 moles. And that is going to equal a pressure of 5.95 atmospheres. And that is going to be the initial pressure that we put in our ice table for the products. All right, so I'm going to keep going. Now I'm going to set up my ice table. So I have 2NO, we have N2 plus O2. And this ice table is going to be interesting because instead of starting with no products, we're starting with no reactants. So we previously discovered that our starting pressure for N2 and O2 is going to be 5.95, and we're going to have zero reactants because we're not told anything about the pressure of the reactants. Now we're going to subtract from the products and add to the reactants because we can't subtract from the reactants if there's nothing there. So I'm going to subtract X from the products and add 2X to the reactants, and we get an equilibrium pressure of 2X for NO, and then for N2 and O2, we get 5.95 minus X. Okay, now we need to calculate the equilibrium pressures, which we can do using Kp, but the issue is that we have Kc. So we need to convert Kc to Kp using the equation that I showed 2 slides ago. And that equation is going to be Kp equals Kc to the RT and times RT to the delta N. Okay, so before we plug everything into our equation, let's figure out delta N. So we know that delta N is going to be the moles of the products that are gases minus the moles of the reactants that are gases. And we're going to figure that out by looking at the coefficients. So each product has a coefficient of 1, and the reactants have a coefficient of 2, which means that the delta N is 2 minus 2, which equals 0. And if we go back to the equation, anything to the 0 power is equaling 1, or anything to the 0 power equals 1, which means this whole part is going to equal 1. So Kp is going to equal Kc. Now that worked out really nicely, and you're not always going to have that in your problems if you need to convert between Kp and Kc. It just so happened that that's the case here. So let's go ahead and set up our Kp expression. We know that Kp, we're going to set it up exactly the same as Kc. It's going to be the pressure of O2 times the pressure of N2 over the pressure of NO squared. And just a note, you can also find Q with pressures. So if we had starting pressures of reactants and products, just like when we have it with concentrations, we'd need to calculate Q and figure out which direction the equilibrium will shift. But we don't need to do that here because we have no reactants in the beginning. All right, so now we're going to substitute in. So I have 0.185 equals, products go on top, 5.95 minus X, and because there's 2 of them, one for N2, one for O2, I'm going to write 5.95 minus X squared divided by 2X squared. And now we're just going to use algebra to solve. So the first step I'm going to do is square root both sides, and then we're going to get 0.430 equals 5.95 minus X over 2X. And now you can use algebra to solve and get that X is going to be 3.20 atmospheres. Okay, so you know that X is 3.20 atmospheres. I'm going to erase some of the work to make room for calculating the equilibrium pressures. As we established earlier, the pressure of N2 is going to equal the pressure of O2, which is 5.95 minus X, which is going to be 2.75 atmospheres. And the pressure of NO is going to be 2X, which is 6.40 atmospheres. So those are the answers that we get for this problem. To reiterate, you do not need to use the mole fraction calculation if you don't want to, if it's easier for you to just find the pressures for each number of moles that you're given. In some cases, it might be easier to find the pressures individually. In some cases, it might be easier to use the mole fraction calculation. I just wanted to show you a new way that you can solve these equilibrium problems. So I hope you enjoyed this video on gas equilibria. Next time, I am going to be talking about manipulating equilibrium expressions. So join me back next time if you need some help with that topic. Feel free to leave any questions or comments in the comment section below, and I will do my best to answer them. Thanks for watching, and good luck with learning chemistry.